Welcome to Communication Hardware Design course. In this course, we will explore key components of industrial communication hardware. We'll begin with PLCs, the brain of industrial automation, and their communication interfaces. Next, we will look at HMI devices, which serve as the bridge between humans and machines. We will also cover industrial networking hardware and finally review best practices for PCB design to ensure reliable communication performance in industrial environments. A programmable logic controller, or a PLC, is an industrial computer used to control and automate machinery and processes. Unlike a regular computer, a PLC is built to handle harsh environments with high reliability. It's called programmable because engineers can write and upload custom logic programs to control specific machines or operations, from simple tasks like turning a motor on or off to managing entire production lines. PLC serves the core controllers in industrial automation. PLCs act as the communication hub in industrial automation. They connect to sensors and actuators through digital I/O for on-off signals and analog I/O for variable signals like temperature or speed. For device-to-device communication, PLCs use serial interfaces such as RS-232 or RS-485. They also support fieldbus networks like Modbus or Profibus, which link multiple field devices in a network. Modern PLCs use industrial Ethernet protocols, such as Ethernet IP or Profinet, enabling high-speed data exchange with other PLCs or control systems. Human-machine interfaces, or HMIs, are the bridge between operators and automated systems. They allow humans to monitor processes, visualize data, and send commands to PLCs or other control units. Through an intuitive graphical interface, often touchscreens or panels, users can track system status, view alarms, and make real-time adjustments. In short, HMIs make complex industrial systems accessible and manageable for human operators. HMIs use graphical user interfaces, or GUIs, to make automation systems easy to monitor and control. The visual display shows real-time process data, alarms, and system graphs on screens, often touch-enabled. Through user interaction, operator can use buttons, sliders, or menus to start or stop machines, adjust settings, and acknowledge alarms. This combination of visualization and control turns the HMI into a powerful tool for efficient and safe plant operations. Real-time monitoring is one of the key functions of HMIs. They constantly receive status updates from the PLC, showing machine conditions, sensor readings, and operational parameters. This live feedback helps operators stay informed about system performance. When something goes wrong, the HMI displays alerts and alarms generated by the PLC, allowing quick responses to faults or abnormal conditions, reducing downtime and improving safety. Industrial networking hardware forms the backbone of modern automation systems. It connects machines, sensors, controllers, and computers within an industrial environment. These devices enable the collection, monitoring, and control of data from various processes, ensuring that information flows reliably between field devices and control systems. Without this hardware, real-time decision-making and automation efficiency wouldn't be possible. Industrial networking hardware ensures smooth communication and data exchange across machines and systems in an industrial setup. Key components include Ethernet switches for connecting devices, routers and gateways for linking different networks, and fieldbus systems for real-time communication between sensors and controllers. We also use wireless devices for flexibility, network interface cards to connect equipment to the network, and IoT devices to collect and transmit data from industrial assets to the cloud. When designing industrial communication PCBs, the first step is clearly defining the requirements. You must identify electrical parameters like voltage levels, current ratings, and signal frequencies to ensure reliable operation. Next, consider mechanical constraints such as board dimensions, mounting holes, and how the PCB fits with its enclosure. Finally, plan for thermal management, since industrial devices often operate continuously and generate heat that must be dissipated efficiently to prevent failure. In the schematic design stage, start with component selection, choose parts that meet your electrical environment requirements. Then, design a clear and logical schematic diagram, making sure every connection is correct and follows your signal flow. Next, focus on component placement. Arrange components so that related signals and group together, minimize trace lengths, and making routing easier later. A well-organized schematic is the foundation for a reliable PCB layout. In the PCB layout phase, start by deciding on the layers stack up. This depends on how complex your circuit is and how much signal integrity you need. You can use single-layer boards for simple circuits or multi-layer boards for high-speed or dense design. When placing components, keep signal paths short and logical. Good placement and routing helps minimize noise, reducing crosstalk, and simplify manufacturing, all critical for reliable industrial communication hardware. This is the end of the course. Thank you for watching.